All right, good morning, all. Uh, yeah, Asa, you should expect it back about 10 minutes ago. When I realized class was coming up, I thought, oh, shoot, I forgot to send that form back. So you should have it in your email. Sorry, I just got a quick answer at chat. Okay, let's see, where are we? Chat window is open, participants window. Uh, okay, that window. All right, can everyone hear me, or can anyone hear me?
Yep.
Yep. All right, sounds good. Joseph Regan, we have a different person who has their, out of 100 and some of you, who has their camera on. Thank you. You're masked, Joseph. Where are you? You're not at home, I guess.
Campus on it.
Oh, all right, nice. At least you can see other human beings. Uh, all right. So let's see, anything. All right, all right. Where is everyone? Is this because it's the Thursday before, but break is only Tuesday, right? There's no, right? It's not Monday, Tuesday, is it? Yeah, it's only Tuesday, so I'm not sure why only about 40% of people are here. Um, all right, let's wait a minute for stragglers, but not too long. Okay, so where we left off, right? We had just derived right, this whole chapter has basically been variations on this equation, the Lorentz force equation, right? If I have a particle of charge q moving with some velocity v, and it's in some b field that points this way, the force on this would be q times v vector cross b vector. And so it would be, and be careful, right? When so a v vector is this way and b points that way, don't do something like this, right? Vectors don't have locations. And so so put them back to back. So v vector points this way, b vector points that way. So green cross red is out of the page, right? And so if instead v vector pointed this way and b vector pointed that way, then v cross b, using my right hand, point this way. And you're only using the right hand rule to choose between the two options. There are only two directions that the cross product can be, because the cross product has to be perpendicular to both of the input vectors. So v cross b can only be this way or that or this way. And you're only using the right hand rule to choose between those options. So we did some things with that. And then we derived last class that if I have a current, a wire with current I, and it's in some magnetic field, and let's say this wire has a length of L. I know, right, the wire can't just abruptly end, but suppose we're measuring the force on a section of it of length L. The wire keeps going, but we're talking about the force on a section of it. And you have, let's say, a B field that goes this way. We derived last time that the force on the wire that follows just from this, from treating the current in the wire as a bunch of charges moving at some velocity, and we derived that it's I times L cross B vector. And then the funny thing is, right, you think, well, how does the length of this thing, how is that a vector quantity? Length is, you don't usually think of as a vector. It is a vector whose size is the length of the wire and whose direction is the direction of the current. And in my mind, it would make more sense to have the current have the vector on it, because that's a naturally vector quantity to me, but your book uses this, puts the vector on L, and so we'll follow that convention. So in this case, L vector is this way, B vector is this way, so L cross B is out of the page. Okay. Yeah, okay, fine. All right, so cross product should be in parentheses, right? It doesn't actually, Eric, it doesn't actually matter. Yeah, I mean, typically I write it this way, but it doesn't matter. You can multiply this by that, or do the cross product and then multiply at the end, because this thing is just a number. Does that make sense, Eric? Is that okay? Okay. So good. So let's do, we did one quick problem. Let's do one that's a little more complicated using this just as an example. So let's suppose I have a triangular loop of wire. And let's say this length is 50 centimeters. This length is 120 centimeters. And if this is let's assume that's a right triangle, then that forces this to be 130 centimeters, right? Okay, and then let's assume that there's a B field coming in. Well, the magnitude of the B field, let's say, is 75 millitesla, 75 10 to the minus 3 Tesla. Okay, let's find the force on all three legs. I'm getting overwhelmed with my color choices here. All right, let's find the force on all three legs. Oh, wait, well, the force on all three legs now is nothing because there's no current running in it. So let's suppose that there's a current, continuing to be overwhelmed with my choice of colors. Let's say there's a current of 4 amps going around the loop this way. So there's a battery plugged in somewhere here. So the current, you have 4 amps, then 4 amps, then 4 amps going around the triangle that way. What's the force on each leg? All right. Let's give these legs labels. So let's call this leg 1, call this leg 2, and this one leg 3. And so we'll just, separately find the force on this leg, and then the force on that one, and the force on that one. And the basic idea of this problem is, look, it's this problem over and over. And in fact, so I meant to say this before, after the second try exam, some people said, oh, well, I did a lot. Some people didn't do better. Some people did better, whatever. But I was asking, in office hours, I was trying to give advice to people who were struggling. And then after the sort of in a shotgun way, trying to just give all kinds of advice and then see what stuck for different people. And then I asked a couple people what helped. And one or two people said the advice, and I don't think I gave this in class, the advice to be very sure that you're breaking down problems carefully or very thoroughly, I should say, or as completely as possible. So sorry, I'm off topic a little, but right, when you see a problem like, I don't know, you have a bunch of point charges and you want to find the electric field here. I think the first thing to do is to forget about this and just go all the way back and think of what would you do if you had 1 point charge and you want to know the electric field at this point P. Go back and think, all right, what did I do for that? And you'd say it's KQ over distance squared in the x hat, if this is positive, in the x hat direction. So you go back and you take a minute and think about this problem. and think, remember that, right, this is the most basic Coulomb's law problem. And then from there, you think, okay, now what if I just had sort of two charges? What would I do there? And then what if I had 3 and 4? So whenever you have any of these problems, so like in the first exam, you had the problem with 2, I don't remember what it was, something like this. Find the potential here. First thing you do is remember, what is the potential near a point? You have a point charge and you're here. What's the potential here from the point charge? And then you step from there and say, what's the potential here from a single line charge? And then you work on that. And you say, okay, now what's the potential from 2 line charges? So you work your way up from the easiest sort of, what's the word I'm looking for? Prototype problem. It's not the word I'm looking for, but the easiest problem of that type, and then work your way forward to the problem you're trying to do. So here, you just think, all right, I've got 3 legs of a triangle. Each one is a wire with current, and there's some angle between the current direction and the B field. And so it's this problem over and over and over. We do this problem 3 times with 3 different angles. Right? So let's find the force on leg 1. So questions so far? Okay, so for leg 1, this one's going to be easy. So the force on leg 1 is going to be I times L vector cross B vector. L vector points, so the current is going this way. So you have a wire of 1.3 meters with L going this way, B going that way. So in this case, L and B are opposite to each other. So this becomes I times L. So we need the vector. So it's going to be L, magnitude of L times magnitude of B times sine of the angle between them. And the angle between them is pi, because L goes this way, B goes that way. So they're in opposite directions. And then this would be, so the direction, let me just put magnitude of F here, because it's going to wind up being 0 anyway. So this thing, sine of pi is 0, and so the whole force on it is 0. All right? Because the current and the B field are in opposite directions, it's 0. All right? Why doesn't one force affect another? What do you mean? I'm not sure what you mean, Liam. Just unmute and ask.
The way in which you're able to add the different charges as if they're independent from one another. Why wouldn't they affect one another?
You're talking about like this thing. You're talking about this problem? Yeah, so that's what's known as the principle of superposition. I guess like all scientific things, it's ultimately experiment that verifies it, right? So electric fields don't they don't interfere with each other and change each other as they sort of pass through one another. I mean, in the same way, the same thing happens. Like if I'm standing here and you're standing here, we can in principle have a conversation, and 2 people standing here and here can also have a conversation, and they talk to each other, and then the sound waves of my voice and your voice cross over each other and pass through these others, and those sound waves superimpose, but ultimately they don't interfere or change each other on the way out, right? It doesn't, if 2 people are speaking at once, it doesn't suddenly change it into a completely different sound. It's just the sum of the 2. And electric fields work the same way. So I think the short answer is that it's an experimentally verified fact. Nature wouldn't have to do it that way, but it does. So that's why we can say, look, the E field here from all of these, just pretend that's the only one, and then that is the only, and that, and each one on its own is the only one. Add the results. They each act independently. Right? But fundamentally, fundamentally, it's an experimental fact. Nature seems to work that way. Okay, so this one, the force on this leg from the B field is nothing. So let's find now the force for leg 2. All right, this one's going to be a little trickier because now the current is going this way. And so for leg 2, now we have something whose direction is this. So it's still I times L vector cross B vector. But now L vector goes this way, and B vector goes this way. And so now I need sine of this angle, that angle theta. So this is going to be equal to, so the magnitude of the force will be I times, well, I need the actual direction. So it's going to be I times L. So L is going to be that times B, the strength of the magnetic field, times sine of this angle. Okay, and that is going to be, so take a minute and do the right-hand rule and figure out the direction of I L cross B. So do it on your own. L goes this way, B goes that way. So do L cross B. Right, so it's into the page. Good, Greg. All right, so it's going to be this amount, and it's going to be in hat. And so that's going to be, so now I need the current, so it's going to be 4 amps times 0.5 meters times 0.075 Tesla times sine of what? What's the opening angle here? Well, sine of this angle is 120 over 130, right? So it's that over that. Sorry, sine of theta is going to be that over that. So it's this times sine theta is equal to 120 over 130. All right. Okay. Good questions on this one. The third leg is going to be the same thing. So if you have confusion, we should clear it up now in this part.
Is the force a direction, or do we not need any?
Oh yeah, it is. It is. I was just testing you, right? So what's the direction? L cross B. L is this way, B is this way. And so L cross B is into the page. Thank you for catching that. So it would be this much in hat. Sorry, hold on 1 second. Sorry, I'm back. So it's this much in hat. All right. So questions on this? Yeah, I do. I teach actually, Brady, I actually stand up because otherwise I just spend all my days sitting. It's not good.
All good, no questions?
Yeah, go ahead. Questions, yeah. Did you have a question, Eric?
No, I said no questions. Thank you.
Oh, okay. All right, fine. So good. So this is, so that's it for this. And now for the third leg, we need to do the same thing. So it's going to be I times L times B times sine of, it's a different angle though. Let's call this angle phi, right? Because for this leg, now we have L going this way and B going this way. Sorry, let me just be consistent. B goes this way. So here's L vector, right? Current's going that way. And B vector goes this way. So now we need sine of this angle phi. All right, so this angle in here, phi, the angle between this B field and this That angle, that's the same as this angle, right? Because you got this and that. If this is parallel to this, if the B field is coming in line with that, so it's coming like this, and so this angle is the same as that angle, right? Because if you have a line like this, and then you have something like, you have two parallel lines like this angle is the same as that angle. Okay, so yeah, so we've got IL cross B, and so that's ILB sine phi. Okay, so that's going to be, and then we're going to need a direction. And what's the direction of L cross B? It's going to be L cross B, which is out. So it's going to be this size in the outward direction. All right, questions so far? Oh, I'm still confused why we aren't using the matrix stuff for the ILB, or does it just work out with sine? You could, in principle, use, I think it would be harder in this case to do with, with the matrix version. The matrix version tends to be needed when you have things that have all three components, but there's nothing wrong. You could do it that way. You'd break L vector into some, like this vector would be purely x hat, and then you would be minus 50, minus 0.5 x hat. And then B, you would break this, which is going at this angle, you'd break it into an x and a y component. So this would have a negative x component and a positive y component. And you could just crank through and do the cross product that way. You'd get the same thing. Yeah. So Asa, yeah. So you can just do it that way if you want. I think it's a little harder in this problem. And there's also one other reason I want to do it this way, which you'll see in a second. Okay, so other questions on this or this angle or anything before we finish? Okay, so it's ILB sine phi out hat. So we need sine of this angle, which is same as sine of that angle. So that's going to be 4 amps times L, which is in this case 1.20 meters, times B, which is 0.075 Tesla, 75 millitesla, 0.075 Tesla, times sine of this angle, which is that angle. So sine of this angle is 50 over 130. And the direction is outward. All right. So now the force total. All right, questions on this so far? All right, rather than, yes, you can plug in numerically and do all of this and do all of that, but look at what you're going to get. First of all, they're in opposite directions. So there's an inward force on this one and an outward force on that leg. And now if you just compare these two things, what you're going to realize is, oh, they're actually identical, right? Obviously, these two terms and those two terms are the same. And in this one, you have 0.5 times 120 over 30. And this one, you have 1.2 over 50 times 50 over 130. So the product of these is exactly the same thing. And one is inward, one is outward. And so the force total is 0. Okay. Oh, slide the page and then never mind. All right. So the total force on this triangle is 0. So any questions on any part of this?
Sir, I have one question about in direction and out direction. And it's in the formula, right? Or just you read that to let us know the direction?
It is from this that I got the in or out. Right? So when you do the cross product of L and B, remember this cross product, the thing in parentheses after you do the cross product, that result is a vector. And so the vector of, if you're doing this, L goes this way, B for this leg, L goes that way, and B goes this way. So L cross B is inward. For this leg, L goes that way, B goes this way. So L cross B is out. Right. So I didn't, right. I didn't get these directions from something other than just this.
Okay, thank you, sir.
Yeah, Daniel, I'll do that in a second. And do you not have to convert the 150 and 30 for the sign? Yeah, 50 over 130, or you can do 0.5 over 1.3. I mean, it's the same. It's just the ratio. So Abby's okay. Oh, I see. I should look for the NVM. Okay. So yeah, so Daniel, why they cancel is, right, if you just compare these things, right, well, one is in, one is out. So they're going to obviously be working against each other. So if this numerical value matches that numerical value, they're going to cancel. So these are the same. And here you have, right, you have a 1 over 130. So that's going to cancel. Right, that's the same in both. So here you have 1.2 times 50. And here you have, which is 60. And here you have 120 times 0.5, which is also 60. Right? So they're going to cancel each other out. And we're not proving it, but you can show that for any loop of any shape, right? I can draw a loop like that and then have a B field coming in any direction. And the total force on this will always be 0. On any closed loop, the total force on it in a magnetic field will always be 0. And you can kind of, if you're trying to, we're not going to do a formal proof, but if you're trying to think about this, you can sort of see it, because the only, right, at this point, let's say you have a current going around this way, right? The only force, right, on this, let's say this little segment here, in which the current is going this way. So you could evaluate the current on this loop by splitting it into little segments and evaluating the force on each little piece of the loop. And when you do that, what you realize is that the little vector step you take from there to there, it has some component perpendicular to the field and some component in line with the field, right? If you take a step, there's some this way and some that way, some in the X hat, some in the Y hat direction. But the Y component of the step doesn't make any difference, because it's in line either against or with the B field. And so it doesn't matter. So it's only really the crosswise portion of your step that creates a force on that little segment of the wire. And so if I start here and I go around in a loop and come all the way back to here, obviously the shadow, think of it this way, the shadow of where I am, if I shine a flashlight this way, the shadow of where I am on this wall, of course, you step out for a while to about here, and then you step back for a while and you wind up here, and then the shadow moves back to here. And so it's really, and it's only those crosswise steps that matter. But if you go in a loop, your crosswise steps sum to nothing. You obviously have to go right the same amount you go left, ultimately, if you're going to come back to the same spot. Yeah, so Asa, can you show visually using the triangle picture why they would cancel? Yeah, okay, right. So in this case, right, that's a good point. Rather than this one, if we look at this one, physically they cancel because the only part of when you're stepping along here, right, and we already said there's in this case, there's an inward force on this leg. Yes, you make all these little steps, but really the only portion of the steps that matter is the amount you travel perpendicular to this B field, which is you really just travel this far perpendicular to the B field. Right? Yes, you're going this far, but the components of your motion parallel to the B field don't matter. It's only the components of your motion perpendicular to the B field. So you really only traveled this far perpendicular to the B field, and then you were at the corner. And now when you go from here back to here, your perpendicular travel distance is really from here to here. Yes, you travel farther than this, but I don't care about the fact that you also moved some in this direct. You moved, this amount in the parallel direction. It's this that matters. And so these two lengths are the same. You move perpendicularly out and then back. I don't care what path you took along here. You could go like this in some crazy zigzag. It's only the perpendicular part that matters. Christina, it's not all symmetrical shapes that have a net force of 0 from the B field. It's all shapes in general, all closed loops. So this is not symmetrical. But if I have a B field like this, the total force on all legs of this will be nothing. Right? If, a loop with a current I coming through it, going around it. So the individual legs have forces on them, but the total force will be 0. Okay. So let's move on to one last thing. I'm glad we spent a while on that loop because it'll quicken the very last thing we're going to do in this chapter.
I got a quick question on the triangle. So
yeah.
I just did that mathematically with the 0.5 and 1.20, but it still shows that there's still an outwards force, even though it's very small. If that makes sense.
No, it shouldn't.
Well, I just did 0.5 times sine of 120 over 130. And then I did.
No. Yeah. Be careful. It's not sine of 120 over 130. Sine of theta is 120 over 130.
Okay.
This is the sine. So Eric, does it matter if there's a connection inside the loop? Yeah, I mean, it would be if you did, I don't know, you'd have to figure out a path for the current. Like if you wanted the current to go like this, I don't know, that'd be more complicated. Like if you had multiple loops but I believe the short answer is probably I think it would still be 0 because each loop would have a force of 0 on it. So yeah, if you had a messier circuit, you had something like this and you had different currents flowing like one of those 2-loop circuits that we did, you'd still get 0 because each leg on its own, all the legs would cancel out. I think. I have to think about it actually. I'm pretty sure it would, but now I'm worried about the fact that if you have this and you have some current here, I'm pretty, right? Because this current is not the same as either that one or this one. I have to think about it. I'm almost sure it'll still be 0, but it'd be I'd have to think about it to prove it. Okay, so let's look at one last thing in this chapter. Suppose that this is good practice for working on the right-hand rule. Let's suppose I have, we're not going to spend a ton of time on this, but let's suppose I have 3, and I'll do my pause to make sure. So that's X and that's Y. X is coming out of the page. Y is going that way. Z is going this way. Let's take a current loop that is flat. So we have a flat loop. All right, and there's a current I that's going around the loop this way. So it goes that way, and then here, and then over here, and this way. And there's a B field that comes this way. And, continues across. I don't want to draw on top of the rectangle, but okay. And then let's say this thing has lengths of, this side has a length of A, and this side has a length of B. All right. Okay. And let's suppose that this thing sits on some kind of spindle, right? So this is sort of fixed here and it can turn like this, right? So it's sitting on some kind of spindle like that. So it can rotate sort of this way. It can rotate in the, right, this point's in the X direction. So it can turn like this. Okay, so let's find the force on, let's label these legs 1, 2, 3, and 4. So there's 1, 2, 3, and 4. So let's find the force on each of those legs. So the force on leg 1 is going to be, so B goes this way, and the current is coming out of the page. Sorry, B goes this way, and the current is coming out of the page. So L cross B, I should really do it like this, right? So the current is coming toward me, and B is going across. And so L cross B is up, right? So out, this cross that will be upward. And so the force on this leg, again, all we're going to do is repeatedly use I times L vector cross B vector. So the force is going to be I times L. In this case, the length is just B, the length of the rectangle, times B, this capital B, the strength of the B field, and that's in the Z hat direction. Right? Okay, so questions so far? Basically, this is just X hat cross Y hat, right? Because the direction of this, the current is X, direction of the B field is Y. So it's X cross Y is Z.
Now, where did little b come from again?
Little b, that's just the length of the
Okay.
rectangle.
Okay, I didn't see that
Yeah.
at first. I'm sorry.
So F2, the force on leg 2, well, this one's going to be easy because the current goes this way and the B field goes that way. So the force is just 0. So the cross product of L and B is nothing. The force on 3, force on leg 3 is going to be, well, now L goes into the page, B goes this way, and so now L cross B is not, L cross B is now this way, so now it's downward. So the force on leg 3 is going to be minus I times B times Z hat. And the force on leg 4, I and B are going, the length vector and the B vector are opposite to each other, so the force is 0. And so again, no surprise, F total is 0. Okay, but I want you to notice something that, and I don't know how much time, you should have done this in 140. So questions so far on this? Okay, so let's look at the torque. Right, so the force is 0, the total force is 0, but that doesn't mean the loop sits still. If you think about it, so here's our rectangular loop, if you look in the camera, right? And it can rotate this way. And what we just found is that on leg 1, there's a force in the Z direction. And on leg 3 over here, there's a force in the minus Z direction. So obviously, if this thing can rotate on this spindle, it's going to. It's going to turn like this. And the force, you can see what's going to happen is as it, I'm going to tilt it slightly this way so you can see. So as it turns this way, there's still an upward force on this and a downward force on that. So it's going to keep twisting until it winds up here. When it winds up here, there's still an upward force on this leg, a downward force on that one. And then there will be forces on these side legs, but they'll be outward. So what's going to happen is the loop is going to twist and it's going to turn and stop here. You could also, if you did that, if it got to here and you wanted to turn it more, you could switch the direction of the current. So when it gets to here, if you flip the direction of the current, now you can, if B field is going this way, if I make the current go this way, nope, wrong way. If I make the current go like this, so I switch the direction of the current, then L cross B is up. So if I switch the direction of the current, as soon as it gets to here, now the force on this leg is up and this leg is down, and it'll twist this way, and then it'll stop here. And I could switch the direction of the current again when it gets to here, and just keep, and if I do that, if I keep switching it, the thing will continue to rotate. Is there a lab video or something that shows all this action happen with real things? Yeah, you can probably do torque on a square, just do torque on a loop of wire. So ASA. The cross product on leg 3 again. Yeah, so leg 3, the current is in the minus X direction, and the B, so the current is into the page, and B is this way, right? So if current is into the page, L cross B, so you have this cross that, which is this way. So it's minus Z downward, right? So that's this one. Is that okay, Dan? Okay, good. All right, so we're not going to go through the whole torque derivation. I just wanted to do enough of this so you can see that when the loop is like this, it's going to twist until, you know, this leg is up. So it's going to twist until it's like that and then stop. And if I switch the direction of the current, then it'll twist till this way. And if I switch it again, I can make it turn back the other direction. And so right, every electric motor basically functions on this principle. And you say, well, how do you switch the current? So if you take a loop of wire, so let me draw it this way instead. If I take a loop of wire, and I have, let's say like this, if I were to wire this straight to a battery, then I would, you know, wire this to a battery, and this thing is in a B field, a permanent B field, so there's magnets around it that, let's say, go that way. Then if I just wire this to a voltage difference, it'll spin and then stop. If instead I were to make these little legs that come out of the loop of wire, if I were to make them sit on, slide along half circles, so they have little loose wires sticking out here and here, and they were to slide along, if you look end on at it.
This is the current goes out here.
So instead, this is wired to positive, and this is wired to negative, and these two legs that come out of the rectangle drag along these two metal plates. Then as it spins, once it crosses this line, the current will switch directions, right? And these two things, essentially most electric motors function on this principle. These two things are what's called brushes. So if you look at motors, and now you'll see motors that say they are brushless, and we'll talk about that in a second. But essentially all electric motors are permanent magnet, and not a single loop of wire, but a big coil of wire. So if you open up any electric motor, they're heavy because they've got big coil of wire. And you basically use F is IL cross B to make this thing turn. And then as soon as it turns and crosses sides, then the current automatically switches directions, and it'll continue to spin. Now, if you look at some fancier motors, so on drones, yeah, so a commutator and brush assembly, Tyler, yes. Okay. So now actually, rather than brushes, if you look, drone motors and most really modern electric motors, if you look at them, they'll say they're brushless motors. So what they do is, rather than having this mechanical thing, which, right, there's friction and energy loss as the brushes drag along the metal plates. So rather than doing that, there's something that tracks exactly the position of this thing, and there's a chip that switches the direction of the current at exactly the right time, rather than wasting energy here. Okay, so questions so far on this? Okay. And any of this stuff, nothing?
Can you just say it one more time because I'm having difficulty grasping the brushes concept and just like that kind of thing.
Yeah, so right, so imagine that right here's our rectangular loop.
Okay.
And so I have a rectangular loop of wire around and around this thing. And then sticking out one end here, and let's just say it's a single loop. So I have a single loop of wire, and I have the end of this wire sticks out a little, and the end of this wire sticks out a little bit.
Okay.
And now what I really want to happen is once I get to here, I want this wire, which has been wired to a positively charged, the positive charge of the battery, I want it to switch and be wired to the negative side now. So how am I going to switch the wire that comes out here? How am I going to now make it wired to the other side? Well, don't wire these things directly to the battery. Wire metal plates to the battery and then have the leg come out and drag along this metal plate, and then it'll switch sides to the other metal plate when you get to here.
Okay, that makes sense. Okay, thank you. Yeah, I wasn't getting that for some reason.
Yeah, so it's just a straight mechanical switching by moving to the other side. Okay. So moving on, so we're going to switch gears into the next chapter, and we're going to try to finding B fields from currents. So this is remember we said the logical order would be first you would learn how B fields are produced from currents, and then you would find the forces that B fields apply to moving charges and currents. But we don't do it that order. We've been saying something is in a B field without ever talking about where that B field might come from. So now we're switching, and we're actually going to talk about how do you calculate a B field from a current, right? So moving charges produce B fields, and moving charges in B fields feel forces. So we're going to start with what's known as the Biot-Savart law. And you sound much smarter if you call it the Biot-Savart law rather than the Biot-Savart law. So the B field from a current, I'm just going to write it down and then we'll dissect it. And be careful, if you look at other sources, the units of this are very different depending. You might see C's in here or no pi in it. It depends on what unit system. E&M has a variety of unit systems, and different sources and books and videos will all use different units. So just be careful about that. I'm going to obviously follow the units that are used in your text. And the open source and Survey use the same unit system. Okay, so this is what's known as the Biot-Savart law. So what is all this? Well, 4 pi presumably looks familiar. This is known as the permeability constant, or permeability of free space. Sometimes you'll see it if you look at older sources. So this is permeability of free space, and it's 4 pi times 10 to the minus 7 Tesla meters per amp. And the first thing you look at and say, well, why the hell do you do that? Why is the constant 4 pi 10 to the minus 7, and then you divide it by 4 pi? Why don't you just write 10 to the minus 7? And that is this unit craziness, right? Because this is used in other unit systems as well. So that's known as mu naught, permeability constant, or the permeability of free space. I is the current. This is the vector. This is the unit vector from current element to the field point. By field point, I mean the point where you want to find the magnetic field. And R is the distance from the current element to field point. Okay, I think to make this a little clearer, what we need to do is just kind of sketch an example, or what would this look like? So suppose I had a wire carrying a current like this. So I have a wire carrying current I. And what I wanted, and what I can tell you is Biot-Savart says that there's going to be a B field, not just here or here. There's going to be B field everywhere from this wire. Just like if I lay down some point charge here, there's going to be an electric field here and a different E field here, depending on the, where I am will tell me how strong it is and what direction it is, the E field from that point charge. Same thing here. There's a current, a wire carrying a current, some weird bent wire. There's going to be a B field at all locations caused by this current. All right. So what does this tell us about trying to find the B field? Let's look at this point here. Okay, so here's our point P. This is the field point. The point at which we want to actually find the field. There's no object here. That's just where the point we're interested in. All right, so this tells us that the B field at this point from this current is this constant. And now I have to integrate over all the different current elements. So what this says is there's a B field here caused by this little segment of current right here. So if I could keep just that and throw the rest of the wire away, there would be a B field here from this little piece. ds vector is the vector that's in the direction of the current and has length equal to a small section of the wire. R hat is the vector from this element to there. So that's R hat. It's in this direction, has a length of 1. And then this distance is R. All right. So if you look at first this looks more intimidating, and then I is just the current I. At first, this looks kind of intimidating because the cross product inside an integral, but if you look at it, you realize it's not really very different from what we did here. You have a line charge and you want to know the E field here, right? The E field is integral of K dq over r squared, integrated over all the current elements here, right? So the E field here from this whole line charge, it's basically there's an E field here from this element, plus an E field here from this element, plus all of them integrated from there to there. And it's a constant, which you could pull out, and the charge on this element, and it goes as 1 over r squared. This is basically, if you look at it, it's the same thing. It's a constant. The current, and the current's the same everywhere in the wire, and it goes as 1 over r squared. The only subtle difference is now you have to worry about the direction by using a cross product, right? Okay. So questions so far? And then we'll do a couple examples of this. Okay, so first thing to notice is that there's a contribution here from this element. There's also a contribution here from this element here. Right, so here's another element of the wire. So there's another, for this element of the current, ds vector points this way. R hat points from here to there. So which one, and then R in this case is this length, right? This element's a different distance from there than this one is. So between A and B, which one has a larger contribution to the B field here? Is it this element A, or element B? Yeah. Any votes for B? Yeah, it's A for a couple of reasons. One, because it's closer, and so your 1 over r squared is smaller. But you got to be careful. For electric fields, that's all that matters. The strength of the field at a spot just depends on how far away you are. But here it also matters the direction of the current relative to the direction of from the current to the field point. So for this element, this guy contributes basically 0 to the B field there because ds goes this way and r goes that way. And so ds cross r is nothing because you have sine of 0. This one will contribute, this will probably be the biggest contributor because this element is, that's why I was trying to carefully lay this point down at a spot where there'd be one clear biggest contributor because this element is the closest and it's also perpendicular. And so the B field here from this element will probably be, this will be the biggest contributor to the B field here. Now, if I said, what's the B field here? That's a different story. Now, all of a sudden, this contributes very little to the B field here because ds is that way. Now r hat is the same way. But now this contributes because ds goes that way and r goes this way. So, right, different elements will contribute different amounts depending on where you are standing. Okay, and let's figure out what's the direction of the, so questions so far? All right, what's the direction of the B field here from this element? I know its size is mu naught over 4 pi times I, and let's say ds and r hat are perpendicular, so that'll just be ds, and that'll be 1 over r squared. But what's the direction? Do ds vector cross r hat?
Would it be
Let's
out
say-
of the page?
Yep, out of the page. ds vector is that way. R hat is this way. ds cross r is out. Good. Okay, now here's a question. What about over here? What's the direction of the B field here from this element? ds goes that way. Now r hat goes this way. So ds cross r hat is in. So what you can show is that any point over here, all of the contributions from these elements, the B field here from any element is going to be out of the page. The B field over here at any point is always going to be into the page. And the amount, of course, will vary depending on how close you are and where you are and the exact shape of that wire. All right, so think about questions, and then we're going to do an actual example of this. Okay, one thing to be careful of, some books, and I can't remember which books do it this way, some books will write this as mu naught over 4 pi integral I ds vector cross r vector over r cubed. I find that a more confusing way to do things, but right, this is the same as that because r vector, the vector from here to here, is equal to r hat times r. And if don't just say, oh yeah, I guess, I don't know, some craziness with r and r hat, pause and think why that's true. The vector r is a vector from here to here. And that is a vector of length r in the r hat direction. So this and this are the same. So if you write it, if you put this in for that, you can cancel 1 power of r and get this. So some books or some things you look at online or wherever you look at things, you may see it as r vector over r cubed or r hat over r squared. I prefer this one. And I think your book does this one, although they may refer to this. That's the same. Okay, so let's do a quick example. All right, let's just find the B field at the center of a current loop. All right, so we're just going to have a loop of wire like this, carrying current I.
Mm-hmm.
And I want to know the B field here. All right. And let's say this thing has a radius of r. And so I don't mean, so the loop is flat on the page, and this point is also on the page. It's not up here. All right, so what Biot-Savart law tells us is that the B field here is going to be mu naught over 4 pi. I'm going to pull the I out. Mu naught I over 4 pi integral ds vector cross r hat over r squared around the whole loop. So I got it. So there's a B. So let's just figure out one element. What's the direction of the B field here from this one element? So here's our D for this element. ds vector looks like this. For this element, ds vector looks like that. For this element, r hat points that way. For this element, r hat goes this way. What's the direction of ds cross r hat for this element? Here, we'll do a poll. Direction of ds vector cross r hat for this element here. Remember, use the right-hand rule only to choose between two options. There are only two directions that are perpendicular both to ds vector and r hat. They both lie on the page, and so your only options are out and in. That means if you voted up, you got to change. Right, so ds vector goes that way, r hat goes that way. So ds cross r is out. Okay. So questions on why that is? From anyone who voted something else? All right, for this one, ds goes this way, r hat goes this way. So ds cross r is also still out of the page. So the B field here from, actually, if you think about it, the B field here from all of the elements, they're all out of the page. All right. So this integral is going to be equal to, and this will be an easy integral to do, mu naught I over 4 pi. Well, let's look at this. This thing covers an angle of d theta, right? The length of this, the magnitude of ds vector is equal to r times d theta. Right, so integrating around this loop, so if this covers some, we're going to go in little steps of angle d theta. So this will be the integral from theta equals 0, we'll start here, around to 2 pi of ds vector, which is r d theta, that's a magnitude of ds vector, times the magnitude of r hat, which is 1, times sine of the angle between them. The sine between ds vector and r hat is always 1, because the angle is always 90 degrees. So that's going to be sine of pi over 2, and that direction is going to be outward over r squared. Right? The distance from every element to the field point is r, so we need the radius of the circle, so it's just r squared. Right? Sine of pi over 2 is 1, and so this thing becomes mu naught I over 4 pi integral theta equals 0 to 2 pi of r d theta over r squared. So let's just call that d theta over r. But of course, r that's constant. That can just pull out of the integral. And then integral of d theta from 0 to 2 pi is just 2 pi. So the whole thing just becomes, and I screwed up. I still need my vector out hat. So the whole integral, when you do that, you'll just get mu naught I over 4 pi r times 2 pi. So it's mu naught I over 2r. And that is in the out direction. Okay, so think about questions on doing this for a second, what we did.
Can you quickly show how you got out hat again?
Yeah, so for this element, I mean, you got to worry about it because maybe it's out one direction for some elements, and maybe these elements are, maybe this element and this element are working against each other, and the total could be 0, right? So you got to be careful of that. So ds vector for this element here, ds vector points this way, up toward the top of the page. R hat goes from the element to the point you're interested in, so it goes that way. So ds cross r is out, or right out of the page. Is that okay, Evan?
So,
Yes, thank you.
So just to follow up on that, so if the R or if the black pen was facing the other direction, then then it would be going in.
Correct.
Okay.
And then, which immediately brings up the question, well, wait a second, R is going the other direction if you're here, but ds is also going the other direction. Right. So basically blue cross black is right outwards here. And as we circle around to the other side of the page of the circle, now ds goes the other way and r goes the other way. And so ds cross r is still out of the page. So these two elements don't work against each other. They contribute in the same direction.
And does your thumb represent DS or R? Like, what do you use? What
Thumb is in the right-hand rule, your thumb is the result of the cross product.
Okay.
Alrighty, and another question, if I may. So
Yeah,
can you
please.
just explain what you did, just how you integrated from d theta over r to
Oh yeah,
mu
so
naught I over 2r?
yeah, so all I did, I pulled the r out, and then
Okay,
that
you
left
pull over
me with-
1 over r.
and then I pull the out hat out. So that just left me with the integral of d theta from theta equals 0 to 2 pi, which is 2 pi.
Okay.
And then I
And
canceled
then-
2 pi and the 4 pi to leave a 1 over 2.
Okay, thank you. That makes sense now.
For the electric field, questions with a ring and distance d above the ring, all the sideways components canceled and the vertical components added. Why doesn't something similar, why doesn't this have something similar? Yeah, that's a good question, right? So think about it. If I had a ring of charge Q, and you say, what's the E field here? What's the E field at this point from a ring of, total charge Q evenly distributed around that ring? What's the E field here? Quick, somebody. Yeah, Yang, and then I'll do that in a second. Right, so the E field here would be 0. Because the E field here from this element points that way. The E field here from this element points that way. So these two cancel. But that's different for magnetic fields because the direction is not the direction from the current element to the field. It's the cross product of the current direction and the direction to the field point. So it's ds cross r. So they don't cancel here, they add. So yeah, the components are just very, so the components are just very different. Let's see, sorry, let me silence this thing. So for the electric field questions, how do we get, Yang, which one do you mean?
I mean, in that formula, we do only have ds times r direction, and how we convert that formula to the sin pi over 2.
You mean this one here?
Yeah.
Yeah, so if you think about, for this element here, ds vector goes like that. R hat goes this way, right?
Yes.
So ds vector, so is 90 degrees between ds vector and r hat. So that's
I got it.
pi over 2 for this element. And then if you look around, all the elements are the same way.
Thank you, sir.
So it's not coincidence that we did this for the B field at the center of a current loop. This integral would not be so easy if you want the B field here, because now, right? I mean, here ds vector points this way, r hat points that way. They're not 90 degrees. And the distance between the the current elements and the field point keeps changing. And so this simple integral, you wouldn't be able, this r would be a function of theta, your distance is a function of theta. This opening angle is a function of where you are. So you'd still integrate from 0 to 2 pi to include all of these elements, but your integral would be much, much harder. So that's why we did this at the center. So an example where the magnitude of ds wouldn't be r d theta. Yeah, we're going to do another example. All right, so questions on this one, and then we'll do one that doesn't work out quite as simply. Okay, so let's try a different example. So all we've done now is we derived the B field at the center of a loop. What about this case? Let's take a long straight wire carrying current I. Okay, so I want to know the B field. So we have a long straight wire I, and we want to know the magnetic field at this point P here. All right, well, so what that means, let's say this point is a distance R away from the wire. Right, so it's an infinitely long wire carrying current I, you're a distance R away from it. What's the B field there using Biot-Savart law? Well, let's figure out what's the B field here from just one arbitrary element. So this, we're going to do exactly the same thing we did with the line charge. What's the E field here? You find the E field here, call this x equals 0, and find the E field here from an arbitrary element that covers width dx, and then integrate to include all the elements to get the total E field here. We're going to do the same thing. We're going to take this little segment that has current I in it, and its ds vector point is like this. It's a little length ds, and it points this way. And I want to know the B field here from this arbitrary element. And we'll say that that is let's call this the origin. This will be x equals 0. And so this element is a distance x up from the origin. And I want to know the B field here from just that element. And then I'll integrate over elements from x equals 0 to infinity, and then maybe double it or cancel it out from the other half of the wire. All right. So first of all, let's figure out the direction. What's the direction of the B field here from this element? ds vector goes that way. R hat is a vector that goes from the element to here and has length 1. So that's R hat. This length is R, right? How far it is from the element to there. And right away, I can tell you this element contributes the most because it's closest. And also ds and R are perpendicular. So when we write down Biot-Savart law, right? So we're going to use this to find the B field there. Let's just find the B field from that one element. So B from arbitrary element. So that's going to be mu naught I, it's the current in this element, over 4 pi. Okay, now we got a little work to do. So we need ds cross r hat over r squared. This distance is capital R. That's how far away we are from the wire. So ds vector is this, r hat is that. So I need sine of the angle between this and that. So I need sine of this angle. But sine of this angle is the same as sine of this angle, right? So I need sine of this. So I need sine of this angle here. Okay. This length is x, that's r, so capital R. So this length is square root of x squared plus r squared. So now we're making progress. So ds vector, so it's going to be the length of this covers some length dx, just like it did here. Cross r hat has a magnitude of 1, so it'll be dx times 1 times sine of this angle. Call that angle theta. Really, it's sine of this angle between this and that, but sine of this and sine of that are the same thing. So that's going to be sine of theta. So there's ds cross r vector. The direction of ds vector cross r hat is into the page. It's going to be in hat. So this whole thing, square bracket turned into this. Divided by distance squared, which is going to be x squared plus r squared. Okay. Okay. All right. So questions so far. This is almost probably the hardest part of the problem. This, as you know from other cases where we've done, setting up the integral is the tough part.
Where is the r hat part and the big bracket at the bottom?
Where is this in this?
Yes.
Yeah. So what happened to it? It's so cross product is magnitude of this, which is that, times magnitude of r hat, which is 1, times sine of the angle between them, which is sine of this angle. So that's the magnitude of ds vector cross r hat. And the direction we did from the right-hand rule. ds vector cross r hat is in hat.
Where did the integral go?
Very good question. Let me answer a shorter question first.
Okay.
Is r hat always 1? So Daniel, right? R hat is the magnitude of r hat is 1, but it's not, but it has a direction. But yes, the magnitude of a hat vector is always 1. That's what you mean when you say it's a hat vector or a unit vector. So dx 1 sine theta is just magnitude of ds. Yes. Dan, yes. Dx times 1 times sine of theta is the magnitude of this cross that. So, right, this is the magnitude of that. This is the direction of that. Right? And then somebody else had a question that I cut off and I've forgotten what it was.
I asked what happened to the integral.
Oh, yeah, thank you. Right, so this is the integral represents the total B field here. This is the B field here just from this one element. This is not the total B field here. This is just the B field here from that one piece. Just like we did here when you did a line charge. What's the E field here? You say, well, what's the E field here from just this one piece? And then you say, well, we don't want that. We want all of them. And so you had to integrate over that result. Right? You had to integrate lambda dx over L, or sorry, lambda dx over the whole length to get all the contributions. Right? Does that make sense, Evan?
Yeah, that makes sense. But in that one we still integrated though. If it was a line charge, wouldn't we still integrate from x equals 0 to x equals L, right?
Yes, right. So we are not, so just this is important. I'm not saying that this is equal to that. This represents just the B field from this. And now we're going to have to take this next step and say B field total. That is going to be an integral.
Oh, you just found the individual B. Oh, okay. And then we're going to have to integrate for the total.
Exactly.
Okay. Thank you. Sorry. I got lost.
No, it's fine.
Wait, so the integral is part of the equation. So like Gauss's law, it's the integral of E times the Gaussian area equals Q enclosed over epsilon naught. And here the integral is just part of the equation to find at one single place.
No, I wouldn't say that. I would say we are really breaking it down to say we really want the integral to include all contributions. But to do it, we take the intermediate step of saying, well, fine, just find the B field from one piece. And then sum over these pieces, sum over this function to find the contributions, not just from this element, but from all of the elements.
Okay, that makes sense now.
Right. Okay, so B total is going to be the integral. So I'm going to do a little cheat. I'm going to say from x equals 0 to infinity of this. Mu naught I over 4 pi, let's get rid of the dx, get rid of the 1, times dx times in hat times 1 over x squared plus r squared times sine of this angle. Sine of this angle is going to be this over that. So that's going to be r over square root of x squared plus r squared. And then, so this is sine theta. And then you worry for a second, because then you say, well, wait a second, what happened? This all looks fine, except how come you're only including elements from x equals 0 to infinity? What about the contributions from all these? And I'd say, oh, right. We should do from x equals minus infinity to infinity, or we can do 0 to infinity and double the answer. Because this element, the partner element here, the mirror image element, ds vector goes that way, r hat goes that way, and so it'll have the same contribution to this will contribute the same to the B field here as this does. And so if you go from 0 to infinity, you'll only get half the result. And so you go from 0 to infinity and then double it. Okay. So when we get back on Thursday, this is the hardest part of this problem. I'm sure this is done in your book. If it's not, just Google search B field from long straight wire and work this out, the rest on your own. And we will also work it out in class on next Thursday. But be sure to, really start on your own, start this problem over on a blank piece of paper to make sure you really understand it. Getting to here is the hard part. Doing the integral, it's a messy integral, we'll just look up, right?
So for this integral, though, wouldn't we have to do a limit as b goes to infinity? Or is this an integral that is so messy that we can just look up that you don't care?
Yeah. I mean, as you come to know so far, the hard part is turning a physical problem into an integral.
Right.
Doing integration is like, there's just a bunch of techniques. It's kind of, you could sort of just train to do integrals. The thinking part is actually turning this applying this to this problem and getting the correct integral to evaluate. Right?
Sure. Thanks,
Yeah,
Jesse.
Asa, there are questions. Yeah, Bio Savar is definitely part of the homework. So, all right, all. Have a good break. It's not a huge, long spring break, but have a good break. And yeah, there are no office hours next Tuesday, but there are today. And if you need to meet or something, just send me an email. Like if you need to meet over break, I can figure out a time. Bye all.